Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous module, we discussed about torsion of open and closed section beams, and we have seen the formulae of torsion of open section beams, and we have seen the formulae of torsion of closed section beams, and we have seen how to solve a given problem when it is subjected to torque in the closed section beams. Now in the present session, we are going to extend our analysis of open and closed section beams, though in the previous modules we've discussed them separately. That is, open section beams which are subjected to bending, shear and torsion, we studied separately, and then the closed section beams which are subjected to bending, shear and torsion, we studied separately. Now usually in the aircraft structures, you will have the components in which the components made of open and closed section beams together. So whenever you have that open and closed section beams, then how the analysis will be done in terms of bending, shear and torsion. So we are going to look at out in this module. So the learning outcomes in this module are the students are able to analyze combined open and closed section beams and then probably solve problems on these combined section beams. So to understand that, and we are going to look into this diagram. So this particular diagram, you can see the aircraft component, and which is comprised of combination of open and closed section beam. And this is the example which we have given for the section of a wing in the region of an undercarriage bay. Okay, so this is the section of wing in the region of undercarriage bay, and in which you can see this is an open section beam and this is a closed section beam, and these two are integrated together, and now it is called as combined open and closed section beam, combined beam. Okay, open and closed section beam. So the analysis, what we thought in the previous one, what we discussed in the previous modules, so the similar procedure will apply here, but what we need to do here it is for this open section, and for this section especially, we have to follow the open section beam procedure, whether it may be shear or torsion of the beams, and for this particular diagram we need to apply the closed section beam. So open section beam procedure we need to consider separately, and then the closed section beam we need to separate find out separately, and then we need to add both the procedures together, so that will give you the procedure for the combined open and closed section beams. So clearly the part of the section is an open. Now if you try to look at this one, the part of the section is an open section, while the nose portion is a single cell closed section that we have seen in the diagram. Now let's try to examine the methods of analysis of such sections when subjected to bending, shear and torsional loads. Now first in this we are looking into bending, and now when it comes to bending, and usually when it comes to bending, we are going to use mx and my bending moments per unit length. So it is immaterial what form the cross section of a beam takes, because the direct stress due to bending is given by the equation, that is sigma z equals to my ixx minus mx ixy divided by ixx iyy minus I square xy into x plus mx iyy minus my ixy divided by ixx iyy minus I square xy into y. So whether the section is open or whether the section is closed, and that is nothing to deal with the bending of the beam, because we concentrate on how the bending moments are applied to the beam. Whether the beam is open or closed, it doesn't matter. So therefore it is nothing to change any changes for this bending. So directly we can follow the procedure of bending of beams, in which you can consider the direct stress distribution due to unsymmetrical bending formula, which is given by this equation. Okay, now coming to the shear loads, and as we discussed about shear center, the shear loads must apply through the shear center of the combined section, otherwise the shear stresses due to torsion also will arise. So we have discussed about shear center, because shear center is nothing but a point in the cross section about which there exists no torsion. So therefore the shear loads here in the combined open and closed section must be chosen in such a way that the shear loads must be applied through the shear center of the combined section. Therefore, and if it is not applied like that, the stresses due to torsion will arise. So where the shear loads do not act through shear center, its position must be found. If the shear loads are not acting through the shear center, then again we need to find out the position of the shear loads where they are acting, and the loading system is replaced by the shear loads acting through the shear center together with a pure torque. Okay, so if the shear loads are not acting at the shear center, then we need to find out its position and where they are acting, and then the shear loads they have to act through the shear center followed with the torque, and therefore the two loading cases are then analyzed separately. One is the shear load procedure, shear loads are the shearing procedure, and the other one is the torsion procedure we need to apply separately. Okay, we need to analyze separately, right? So again we assume that the cross section of the beam remains undistorted by the loading. So that is one more condition. Now when it comes to the torsion, so generally in the torsion of composite section, the closed portion is the dominant since its torsional stiffness is far greater than that of the attached open section portion, so which may therefore be frequently ignored in the calculation of torsional stiffness, and the shear stress should however be checked in this part of the section. So we have seen the diagram, that is one is the nose portion which is closed and other one is the open section, and in this closed section will have greater torsional stiffness when it is compared with the open section. So torsional stiffness. So torsional stiffness is defined as it is a product of Gj, that is the modulus of rigidity, and the polar moment of inertia, that is the torsional stiffness. So torsional stiffness. So the closed section beam and will have a larger torsional stiffness when it is compared with the open section beam, and therefore sometimes in the analysis you can neglect torsional stiffness of open section beams. Okay, but the shear stresses should be considered for both the closed section beam as well as the open section beam. Now so after knowing this bending, shear and torsional effects on the combined open and closed section beams, now let's look into a problem and see how we are able to calculate for the combined open and closed section beam. So determine the shear flow distribution in the beam section as shown in figure. When it is subjected to a shear load in its vertical plane of symmetry, the thickness of the walls of the section is 2 mm throughout. So he has given a shear load that is 100 kilonewton, that is SY, and it is applied in the vertical plane of symmetry, and he has given the thickness of all the walls as 2 mm. Now if you try to look at it in the diagram, so there are panels 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is also open and closed section beam, combined open and closed section beam, in which the panels 3, 4, 5, 6 is regarded as closed section, whereas 1, 2, 3 is regarded as one open section, and 6, 7, 8 is regarded as another open section. Okay, so combinedly it is one closed section followed by two open section. So it is a combination of both open and closed section beams. Okay, so to analyze this, and as he asked to determine the shear flow distribution in the beam, so what do we do is, and this given diagram is having vertical axis of symmetry, but it is symmetrical about vertical axis. So you can analyze for this beam either left side or right side of this particular diagram, so that the analysis can be extended to both sides of the beam. Okay, and if you look at into the formula of shear flow distribution, if you can remember, and the formula for this open and closed section beam is nothing but minus C cyclic integral of integral 0 to S into T into X into ds minus capital D integral 0 to S T into Y into ds plus QS naught, in which from here to here the formula is for open section beam, that is QB open section beam, and this is additional constant shear flow which we will add for the closed section beams. Okay, so if the closed section beam is there, we'll consider entire formula, and if the beam is open section, then we'll consider only up to here. So clearly from the diagram you can see for the panels 1, 2, 3 or 6, 7, 8, we're going to use the formula QB. From here to here straight away you can follow the shear of open section beams, and then you can find out the shear flow. Whereas for the panel 3, 4, 5, 6, we have to add QS naught, and then you have to make a cut somewhere in the section and there calculate the rest of the open section shear flow, and then you have to take moment about a suitable point, and then you can find out the shear flow in closed section beams. Okay, so that's how we solve this problem. Okay, and here we use C and D, and C and D are nothing but the constants, where C is nothing but Sx Ixx minus Sy Ixy divided by Ixx Iyy minus I square xy, that we have derived the formula in the previous sessions. And then the constant D is nothing but Sy Iyy minus Sx Ixy divided by Ixx Iyy minus I square xy. Okay, so this is a constant D. Now clearly from this diagram, and since the given section is symmetrical about the vertical axis of symmetry, and we can assume, we can take Ixy, that the product of inertia is 0, and also only the vertical shear load that has given 100 kilonewton, and he has not given any horizontal shear load, so you can assume Sx also 0. So by considering Sx equal to 0, Ixy equal to 0, our formula reduces because constant C. So Ixy is 0, Sx is 0. So finally this constant C goes to 0. And if you look at a constant D, then here Ixy is 0, here Ixy is 0, and you left with Sy into Iyy divided by Ixx into Iyy. Again in this Iyy gets cancelled. So you left with the constant D, that is equals to Sy by Ixx. So the formula for shear flow reduces to directly Q equals to, and C is 0, and completely this term is 0, and D is nothing but minus Sy by Ixx into cyclic integral of 0 to S T into Y into ds plus Qs naught. Okay, so this is the first equation you can consider for calculating the shear flow distribution for either open or closed section beam. Okay, so now in this formula, what you can see here is, to start with this problem, first of all we have to calculate the moment of inertia Ixx. Okay, so moment of inertia Ixx you have to calculate for the complete section, that is 1 2 3 4 5 6 7 8, up to 8 you can consider, complete all the flanges and the web you can consider, and then you have to find out the moment of inertia about x-axis. So we know that to calculate the moment of inertia about x-axis, we should know the position of centroid, and first we have to calculate the position of centroid, that is CG position, and then you have to, since the given figure is symmetrical about vertical axis, so if you find out y bar, then it is sufficient, so that you can mark y bar in the axis, vertical axis of symmetry, like this, which is shown here. You need to calculate this y bar, and then once this is marked, then it is easy for us to calculate the moment of inertia about x-axis. So if you look at that y bar, and we know the formula for y bar. So y bar is equals to summation ai yi divided by summation ai, like a1 y1 plus a2 y2 plus a3 y3 and so on, divided by a1 plus a2 plus a3. Okay, so if you look at into this one formula for y bar, and if you look at for example, let's try to consider the bottom, top upper layer as the reference axis to calculate y1 y2 y3, and a1 y1. For example, if you look at 1 2, so area of 1 2, there is nothing but what, 100 into 2 is the thickness, so area of 1 2 is 200, and then its y distance from the center of this figure from here to here, it is 50 mm, so we'll take 50. Similarly for 7 8 also you are going to get similar, and then we'll multiply by 2. Okay, so that is what it's shown here. So 100 into 2 into 50, like that you got 2 cells on the either of the sides. Okay, so 100 into 2 and 50, and like that you got 2 cells. Similarly the next one 2 3, so 2 3 is also, length is 100 and thickness is 2, so you are going to get 100, area is 100 into 2, that is 200, and its y distance is 0, so no need to consider for all 2 3 3 6 6 7, because its y distance is coinciding with the reference axis, so no need to consider for that. And consider looking for 3 4, so 3 4 is 200 mm, so 200 into 2 is the area for this one, and its y distance from the center of this one from here to here, it is 100. Like that you got another one, that is 5 6 on the other side, so you have to multiply it by 2. Okay, so that you will get for 3 4 as well as 5 6. Now coming to this 4 9, again 4 9, that is 100 distance and 2 is the thickness, so you can write 2 into 100 is the area, and then its y distance from here to here, that is nothing but 200. Like that you got 2 beams, 2 flanges, that is 4 9 and 5 9, So you can multiply by 2 and divide by total area, all the areas, and you can see here total area. So if you try to find out like this, and you're going to get y bar as 75 mm. So now this 75 mm you have to depict in the diagram. Okay, so if you look back, and so here it is 100 mm. So somewhere here at the 3/4 of the portion from the upper surface, you can represent this one, and you can write this y bar as 75 mm. Okay, so from here to here, from the upper layer up to 75 mm, you are marking the centroid, and then you can probably denote x-axis and y-axis system. Okay, and now once you calculate the y bar, and then you have to go and find out ixx, moment of inertia about x-axis. So the moment of inertia about x-axis also, here what you can do is, so since this is vertical, having vertical symmetry, so you can consider for the half of the section, either left half of the section or right half of the section, and then you can calculate multiplying by 2. Okay, so if you try to look at this one, and let's try to do for 1 2, and for panel 1 2, and I'm writing here, so BD cube by 12, B is nothing but 2 into depth is nothing but 100, so we'll write 100 cube by 12 plus area, that is 2 into 100 into y bar. So y bar, and what is a y bar that you have to take? That is a total figure centroid is here, and the first figure centroid is here, and this distance is 75 mm. Okay, and distance from here to here it is 50 mm. So 75 minus 50 you have to subtract, then you are going to get 25. So you will get 25 square. That is for panel 1 2, that is web 1 2. Similarly for 7 8 also you are going to get the same, so you are going to multiply by 2. So that is what is given here. Okay, so that is completed. And for this one, next if you try to write for 2 3, and you can write in the similar manner, and for 2 3 what you can write is again BD cube by 12, and so B is nothing but 100, and then 2 cube by 12 plus 100 into 2 is the area, and its distance from the centroid of this one to the total figure centroid is 75. So you are going to write 75 square. But the problem here it is the 2 cube, that is 2 is the very small thickness, that is, and its cube can be neglected in the analysis, and it can be substituted 0, and like that you got another panel 2 3, that is nothing but 6 7, and you can multiply by 2. Okay, so finally you are going to get 2 into 2 4, 4 into 100, that is 400 into 75 square you are going to get. And similarly for 3 0 and 06 also you are going to get the same one, and you can multiply by another 2, and therefore the analysis what you are going to get here is 400 into 2 into 75 square for the panels 2 3, 3 0, 06 and 6 7. Okay, and then finally what we left with is and other one, that is, and we have here, because here we got 3 0, 06 and then 4 9 and 5 9 also we are having, and then probably what you can do here it is 2 3, 3 0 and 4 9 also you are going to get similar one, but the slight change. And then coming to this 3 4 is important again here. How to calculate for 3 4, and again BD cube by 12, B is 2 and depth is nothing but 200 cube by 12 plus 2 into 200 is the area into y bar square. So the center of this one will be somewhere 100 mm, and from here to here it is 75 mm, and you can clearly see here it is the distance between this centroid and this centroid is 25 mm. So you will write here 25 minus 25 whole square. So anyway it will become positive. Okay, so this is how. So like that you got another panel, that is 5 6 panel, and you can write, and therefore so in this way if you calculate moment of inertia, and then you're going to get the moment of inertia as 14.5 into 10 power 6 mm power 4. Okay, so once you get this moment of inertia, and then now you can start solving for the shear flow. So the shear flow, the formula which we already seen, that is Qs equals to minus Sy by Ixx integral 0 to S T into Y into ds plus Qns naught, that you can consider as first equation. And then now after knowing this one, now we have to do the shear flow distribution separately for the open section and closed section beams. So if you look at into open section beams, that is 1, 2, 3 and 6, 7, 8 panels. So any one you can do either 1, 2, 3 or 6, 7, 8, so that the other one will become same like from the symmetry. So for the open section beams, this QS node does not exist. So the formula limits only up to here, that is minus Sy by Ixx integral 0 to S Ty into ds. So now what we are doing here, and if you look at the diagram, okay, so S1 is considered as distribution. Now in the formula we have T into Y into ds. So just we need to substitute what is Y. So Y from the diagram, Y we need to measure from the centroidal distance. So therefore what we are going to substitute here it is, and Y for Y, let's look into the diagram. So S1 is considered from here to here, and then the centroid is here, and the distance, the total, the center of this diagram will be here, and which is a distance of 50 here, and the total figure centroid from here to here it is 75 mm. So therefore this is 50 mm. So the difference what you got from here to here it is 25 mm. Okay, so why we have to substitute it as, and 25 minus S1 you have to substitute. Okay, 25 minus S1 you have to substitute for Y, and therefore when you try to substitute it in the formula for Y, minus into Sy is nothing but 100 kilonewton, and then divided by minus Sy divided by Ixx is 14.5 into 10 power 6 integral 0 to 1, and 2 is the thickness, and then S1 that is minus 25 plus S1 you have to substitute here, and as we discussed here, that is 25. S1 is greater here, so you have to consider S1 as positive, and then minus 25 you can consider. Okay, so plus S1 minus 25. So here we are substituting here plus S1 minus 25 into ds1. Then if you try to integrate this, and this minus 50 into S1 you are going to get, and S1 will become S1 square. So clearly for panel 1, 2, minus 69 into 10 power minus 4 minus 50 S1 plus S1 square, you are we are getting the distribution, and you can see from this distribution that we are getting the parabolic curve, that is we got S1 square, that is the degree is 2. Okay, and then we got Q12, and then you can substitute for the open section at S1 equals to 0. When you substitute in this equation, you are going to get Q1 equal to 0, and at S1 equals to 100 mm, you can substitute in this equation, and then you are going to get Q2 as minus 34.5 Newton per mm. Okay, and similarly that is for wall 1, 2. Similarly you can do for wall 2, 3 also by substituting its distribution as considering distribution as S2. So when you take the horizontal distribution for S2, its Y distance does not change from here, because from here to the center of the total figure it remains constant, that is 75 mm. So straight away you can consider Y distance as 75, and then you can substitute over here in the formula, that is minus 16 and 10 power minus 4 for the wall 2, 3 integral 0 to S2 2 into 75. For Y we are substituting 75 ds2, and for which we need to add the open section shear flow, that is the starting shear flow which we need to add, that is nothing but Q2 we need to add for this formula, that is minus 34.5. So if you try to integrate this, you are going to get Q23 equals to minus 1.04 S2 minus 34.5 you got. Okay, so again if you look at into this distribution, S2 is having power 1, so you are going to get linear curve for the wall 2, 3. Okay, for wall 1, 2 we got parabolic curve, and for wall 2, 3 you are going to get linear curve. Okay, so this is and again you can substitute the boundary condition at S2 at 2, S2 equal to 0. So when you substitute in this equation, you are going to get Q2, that is equals to minus 34.5 Newton per mm, which is similar like the previous one. Now at 3, S2 is equals to 100 mm, and when you substitute in this 1.04 into 100, that you are going to get 104 minus 34.5, then you are going to get Q3, that is equals to 65.5 Newton per mm. So that is what you are going to get, 65.5. 65.5 Newton per mm, you're going to get Q3 value. Okay, so again Q1 equal to 0, so that you can get Q8 is equals to 0 because of symmetry, and Q2 equals to 30 minus 34.5, and therefore you can make it equal to Q7. Okay, and here we got Q3, and this is also equal to Q6 from the symmetry. So for the open section beam, which is shown in figure 1, 2, 3 and 7, 8, 9, all these, that is Q1, Q2, Q3 values are found out, and 6, 7, 8, 7, 6 also found out from the symmetry. Now we left with the closed section. Now let's look into this closed section problem. And the analysis of open part of the beam section is complete, and since the shear flow distribution in the wall 6, 7 and 7, 8 follows symmetry. So to determine the shear flow distribution in the closed part of the section, what we need to do is we need to cut any one section in the closed part of the section, and at some convenient point, and obtain the QB or open section shear flows for the complete section, and then taking moment about a suitable point and make it to 0, so that you will come to know what is the additional constant shear flow. So the final value of the shear flow must be 0 at the midpoints of walls 3, 6 and 4, 5. So if you look at that diagram, the final value of the final shear flows must be 0 at the midpoints of the walls 3, 6 and 4, 5. So let's look into 3, 6 and 4, 5. So 3, 6. So 3, 6 and 4, 5. So this is that is the final shear flow must be 0 here and here for the closed section. Okay, so that's we will see here. Yeah, hence now we are cutting the section, trying to calculate O3, that is for the, and if you consider panel like this, and this will be 3O, and this is 4, 5, 6. So we are trying to calculate for O3 and considering the other wall is open. So therefore it becomes, Q03 equals to minus 69 into 10 power minus 4 integral 0 to S3, and you can consider the distribution as shown in the diagram. S3 is taken from here to here, that is S3. So that if you try to substitute for Y, again it is constant, so you can substitute directly 75 mm. Y is constant. So therefore here 2 into 75 into DS3, and you got Q03 equals to minus 1.04 S3. Okay, again you can see clearly that here you got you're going to get the linear curve. Okay, and Q3 what we got from the previous analysis, and that is nothing but 65.5, and if you try to substitute, multiply by 1.04, and Q03, that is 1.04 S3, and if you try to substitute for the limits, that is at O, that is S3 equal to 0, and at 3 boundary condition, at 3 you can substitute S3 equals to 100 mm, and when you try to substitute in this, you are going to get Q3, and Q3 you are going to get 1.04 into 100, that is nothing but 104 Newton per mm, which is negative. So that is what shown here. So that is minus 104 Newton per mm, and it follows that for the equilibrium of the shear flows at 3, the Q3 in the wall 3, 4 must be equal to minus 138.5 minus 104. Okay, so if you try to look at for the wall 4, that is 3, 4, then it must be equal to minus 138.5 minus 104. So total together it should be minus 242.5. Okay, then if you try to look at for the panel 3, 4, and for the panel 3, 4, Q34 equals to minus 69 10 power minus 4 integral 0 to S4 you can take, and Y distance you can substitute from the centroid, you can calculate, and it is nothing but 75 minus S4, and then this minus 242.5 you have to add up for that one, because the 3 is the open section shear flow, and because Q3 earlier we got for the formula Q3, how much we got here, and it is not, in fact it is not 65.91, this is becomes 138.5 minus 1, because both are minus, so you got Q3 as Q3, you got this as minus 138.5 Newton per mm. Now this Q3 must be added to the Q3 value what we got here, that is minus 138.5 minus 104 what we got from here. So both together it is minus 242.5. So when you try to solve for Q34, this 245 will become the starting shear flow that you have to add for when you calculate in 34 shear flow. So therefore Q34 that is equals to minus 16 and 10 power minus 4 integral 0 to 4, 2 into y distance you can substitute 75 minus S4 into ds4 minus 242.5, and which gives after integration you will going to get Q34 equals to minus 1.04 S4 plus 69 into 10 power minus 4 S4 square minus 242.5. So here you can see S2 square, and again it gives the parabolic curve what we got. And then examination of this equation 6 shows that the Q34 has a maximum value of 281.7 Newton per mm, because you can substitute at 3, you can substitute S3 equal to 0, and at 4 you can substitute S3 equals to 200 mm, and when you try to substitute this one, you're going to get the maximum value that is equals to minus 281.7 mm at S4 equals to 75 mm, and also you're going to get Q4 equals to minus 172.5 Newton per mm. So finally, the distribution of the shear flow in the wall, that is other wall, that is 9-4. If you try to look it into this one, 9-4 or 4-9, you can find in a similar manner, and that you are going to get this as minus 69.10 power minus 4 integral 0 to S5, 2 into minus 125, because 75 is above centroid, the y distance is 75, and below centroid it is minus 125. So if you try to substitute this, and you are going to get 2 into minus 125, that is equals to Q94 equals to 1.73 into S5. Again at 9 you can substitute S5 as 0, so that it will become 0, and at 4 you can substitute S5 is equals to 100 mm, and when you try to substitute like this, and you are going to get Q4 that is equals to 173 Newton per mm. In fact, okay, so this is how we are going to calculate the 173 Newton per mm, that is the Q4. This is how we try to calculate the shear flow in open and closed section beams. Okay, so that's all for today's class. We have seen combined open and closed section beams, how they will be different for bending, shear and torsional case, and how the analysis will be taken out when you try to calculate the shear flow distribution for open and closed section beams. So thank you everyone for watching, and in the next session we are going to see the twist and warping of the cross section. Thank you.